Yay, okay, we haven't done this in a while. Got the right answer. Yes. Okay. Okay, do now. Yesterday we discussed the first type of improper integrals. What features made them improper? Manny. I think I know you know what you're talking about, but I want you to phrase it differently. Okay, that's better. Yeah, if either one of the limits of integration is infinite, either or both, okay, then it's what we call an improper integral. That's the type we talked about yesterday. So, so it's either a lower limit of integration of negative infinity and upper limit of integration positive infinity, or both. We haven't tried one of those. In fact, that's what we're going to do as our challenge. But so they're easy to recognize. You'll see a limit of integration. You'll see an infinity with one limit of integration. So now, do you remember the three steps that we used? Yeah. Oh, yes. Okay. So we're going to rewrite the equation to include L. So we're going to replace. Yeah. Place whatever, wherever you have either the negative infinity or the positive. Right. With L, but you can use A or B or whatever you want. And then I stands for integrate. So you'll actually get the antiderivative, plug in upper, lower, and subtract. And T. And we'll have it. Okay. What I want us to do, because we didn't get to one yesterday, where both limits of integration were infinite, right? We had just. Is that you can't do it? Oh no, you can. Oh, and especially since we have a little hint there. Oh, yeah. Wait, Melly. Okay, guys, listen. Just breaking it up. It's the definite integral from negative infinity to zero, and you could technically break it up at any number you want. It's just zero is just handy. Okay. So now we just could get each of these separately. We can RIT each of these separately and add our two answers together. If they're both finite, if it does converge. So why don't you try to do that? You can't? Yes, you can. Now, if you want to keep it all together as a sum, you can replace one with A and one with B, or you can just replace them both with L and just do them separately. Just draw a line down the middle. And just add your answers. You want to do it like that? Yeah, well, I'm just going to do, I'm going to make them both L. Like, in other words, I'm just going to define each of these separately, because we can do that, right? And so we'll just do the RIT on each one. Oh, yeah. I'll just rewrite each of these terms down, then we'll add answers. So we got to replace, and guys, if you don't want to do them separately, if you want to keep it together, you would have to call one of them A and replace the other one with B. But I think for the class sake, it's easier to do both of them and just do them separately. Step one, we messed up on step one. All right, had to replace infinity with negative infinity with an S. Okay, step two. So for each one of these, we want to derivative, plug in upper, lower, and subtract. So what is the antiderivative? Oh, I'm going to break my eye. Is it an LN? Is it U prime of U? Inverse tan. Yeah. Yeah. Uh, we'll work on this one on the left first. I mean, they're the same thing. Or maybe I'll do both at the same time. That's crazy. And we still have to plug in upper and lower and subtract. Inverse tan of 0 minus inverse tan of L. This is the inverse tan of L minus inverse tan of zero. So we've needed to it over 3 steps. We've integrated. We have to now. What do you want to do? You want to, what's 0? The inverse tan of 0 is 0. If you want to do that now before we take the limit, we can do that. Okay, so let's do that before we actually take the limit. So the angle of tangent is 0. That's what that means. If you think about the tan, and you can only think about the tangent between negative pi over 2 and pi over 2. Remember, tan looks like this. You got to think about what is the angle between negative pi over 2 and positive pi over 2. The tangent is 0. 0. Okay, this is just 0. So we have, so the inverse tan is 0, the angle tan is 0. It's a function. There's only one answer. That's why you can't look everywhere on the number line. You're restricted. And then that would be the same over there. Because we got to talk about. So we're going to do it both separately. We're up to the step, right? Because L stands for different things. I decided to do it separately. Over here, L is going to, for this one, when I take the limit now, L is going to approach negative. For the other one, L is going to approach positive. Okay, so we're going to take the limit. So for the one over here, we're going to take the limit. In this one, L was approaching negative infinity. You can always have, I'm not going to write the zero minus. It's just negative tan of L. And the other one, when you take the limit, we have the limit as L approaches positive infinity. And here we have just the inverse tan of L. Now let's think about what this is asking. They want us to find, let's do that one first because it's positive. What is the angle? What is the angle of tangent approaching infinity? Think about your tan graph between negative pi over 2 and positive pi over 2. What is the angle? What's the angle tangent pi over 2? Okay, so this is pi over 2. And this one, yeah, this is the same. You're finding, remember, it's the inverse trig function. You're looking for the angle. And now it's and the angle. We have negative, so I'm just going to leave that. Okay. But the angle of tangent is negative infinity. That would be negative pi over 2. So we have negative, because that was here. That was just there. That was, and then the angle of tangent is negative infinity. That's negative pi over 2. So we get pi over 2. So is it just, you add them together, you get pi. Isn't that cool? Now, I want to think about what does this graph even look like to begin with? Does anyone know what the graph of y equals 1 over 1 plus x squared looks like? We are getting answer pi. I want to make sure that kids at home see that. Um, the, the graph of y equals, separate to come up with some kind of sense of what we're talking about here. Remember we were finding the definite integral from negative infinity to infinity of 1 over 1 plus x squared? Think about what that means. If you graph, like when y is 1 over 1 plus x squared, well, when x is 0, y is 1, right? And as x gets larger and larger as you go this way, what's happening to the y value? If they're smaller, are they ever going to be negative? No. Zero, right? And then what about on the other side? Same thing. No, this is slow. But we just found is if you were to collect the area underneath this curve all the way from negative infinity to positive infinity, look at pi. What? That's crazy. Come on, that's crazy. I know, very hard. I can't even believe it. I can't even believe it. You just keep collecting there. I know. This is freak worthy. Definitely freak worthy. Okay. Today, I'm going to go, maybe I should do the homework problems first. Let's do homework problems, and then I'm going to talk about the second type of improper intervals. Uh, yeah. Okay, number 1. Did anyone get a half? That's nice. Get one right. Number 2. 1 over 81. No, you didn't. No. Everybody but the right answer? Okay. That is part of history. Okay, so that was 2, 1 over 81. Number 5. Now, I don't have the word. Oh, look at this, the key. It is 5. Now, you could have used the quick way to do it. You remember that? If you're taking the definite integral from 1 to infinity of 1 over x to the power, when that power is greater than 1, yeah, it has to be from 1 to infinity. But yesterday we showed that it'll always be 1 over the power minus 1. So if you just use that, you take 1 over the power minus 1, you get 1 over 0.2, which is 5. So that's kind of nice that this one you didn't even have to do it out because we had that we derived like a little formula how you take the definite integral. Oh, okay. Okay. All right, the next one. 8. What's the answer? Oh, diverges. Do all that. So when you start collecting the area under this one from the 0, what was it from? 0 to infinity? It is just going to, that area is just going to blow up. It's just going to go up to infinity. That's what it's doing. 12. This one. Okay, we can go over 12. Anyone get one? A couple people got one? One person. Okay. Okay. We got a few kids. We'll go over number 12. You know what? Well, was that the last one or no? Okay. So that's, yeah, I know. I hit a button and make it blurry. All right. So for this one, it was the definite integral from 0 to infinity of, okay. So first step, R. So we replace the infinity. We take care of that. So we're taking definite integral from 0 to L. I'm sorry. I bet this is where you just said, nah, I don't feel like integrating that. Yeah, I know. But, Ellie, do you remember a recent topic that we covered that would allow us to integrate this? Tabular. So let's do that. A little turbo part. That's all that is, right? You don't have to write that, but So, Leibniz. Which one is going to be the U? Remember we used Leibniz? The X. The power comes before the E. T comes before E in Leibniz. So we have X, so that must mean that E to the negative X will be our dV. We just don't include the dx. Now, the first column, we differentiate down to 0. So that's no problem. 1, 0. The other one, don't differentiate that one too. Although, it's not right. But you have to take the antiderivative. To take the antiderivative of e to the negative x, you would need a negative 1. Right? So you'd have a negative on the outside. What do you get? Negative x. And then it'll go positive again because you would need another negative 1, so you'd have to come here. Okay, so that's part of it. And then remember, we work on the diagonal, positive, negative. So let's write down this antiderivative. What's the first term of my antiderivative? X e to the negative x. Okay. And what's the next term? Right. Now it's a definite integral, so we're going from 0 to L. We're going to plug in the L. So it's negative x e to the negative L minus. Oh, whoops. Hello. Sorry about that. Negative L. Plugging in the L first for the x, and then we'll plug in the 0. Negative L e to the negative L. E to the negative L. Well, wait a minute. I just minus. Oh, well, yeah. I think we gotta be careful. Sorry. If you plug in the lower limit, okay, this first term is 0. The 0 times that is going to be 0. Right. Minus e to the 0 is minus 1. So is that? Sorry. Oh, yeah. Correct. Right. So instead of having minus negative 1, let's just write plus 1. And the other thing I would like to do here before we take the limit, without the negative, I don't want the negative exponents anymore. I want to rewrite this. So the first term, rewriting it, e to the e. Right. So we can write this as negative L over e to the L minus e to the L, and then you said it was plus 1. Okay. You could put it together. You want to, oh, we can make this as lovely as you want. Yeah, you want, so, yeah. I mean, we can pull out a negative 1. This is pretty enough, though. Okay? Yes. So, now we just take the limit. What was L approaching? Oh, wait, I want to write L. No, I wanted T. What am I saying? T. Okay, T is in the other column. Okay, so now we want to take the limit as L approaches, what was it originally? Infinity? So negative L minus 1. Oops, what am I saying? L. I'm sorry. Now, just a minute though, because I want to know how you guys knew it was 1 right away. Okay, you're not thinking of like that rational function rule, are you? Because, I mean, you're right, but I just want to make sure it's for the right reasons. If you just tried, if L is approaching infinity, do you guys see we'd have like infinity over infinity, negative infinity over infinity? What? Who do you call when that happens to see what it is? And then when they don't answer, will be down, right? So even if you didn't realize that you had a slow-growing function over a fast one, which is always going to give you 0, as it approaches infinity. So if you didn't realize that and you didn't do it that way, you could always have used L'Hopital's. Okay. I just thought this is a fun problem because we bring in all our old friends here. So yeah, we could use L'Hopital's, and that would give us 0 plus 1. Let me just get out of the way. With that, yeah, when you get infinity over infinity or 0 over 0, That's the indeterminate type. You can replace the numerator with its derivative and the denominator with its derivative. Okay, you ready for the second type of improper integral? Nice. I like the class today because we're not just all in the back, and it's nice. At home, don't come back. I'm sorry, I couldn't hear you from up here. Was I not allowed to say that? All right, ready, guys? All right, let's look at the second type of improper integral. Second type. So the first type, the limits of integration, those are nice, easy to spot. This type, the actual function goes off to infinity, the integrand. So, you might not, if you're just given the definite integral and you don't see the graph, you might not realize this. Right? So if you have, I'm just, do I have a picture now? No, I'm going to draw pictures. Okay. So you could have a situation where you're asked for the definite integral from A to B. We'll just roll through three little pictures here. Let me fit three in here. Right? A to B. Put a little A and B in all of them. Okay. So, three. Three's good. This one I put so far. Three. Um, and it's going to look like a nice, they're going to say, okay, evaluate the definite integral from A to B. And A and B are going to be normal, finite values. But what follows is some function that's got one of these three things going on. You either have a vertical asymptote on left endpoint, maybe something like that. So you're trying to gather the area underneath it from a vertical asymptote to the other here. Or you could have that vertical asymptote on the right. It doesn't have to go to positive infinity. I could have made it go to negative infinity. Yeah. And then what do you think the worst case scenario would be? Yeah, right? That would be nightmare. I don't know. Well, I know I should make one negative, but I want to just, yeah, this should be. How do you tell if you don't have a graph in front of you if a function has a vertical asymptote? What kind of functions are going to have those vertical asymptotes? Rational functions. Jared! Oh no. Okay. Come back. Come back. Okay. You know you have a vertical asymptote if any value of x makes the denominator 0, but not the numerator. So when you see, um, if you see you have something like you were just saying, where's that going to have a vertical asymptote? A 2. So if you're asked to find a definite integral, let's say from 2 to 4, that's improper. What else could be the limits of integration where it would still be improper? Like, let's keep it 1 over x minus 2. We know it has a vertical asymptote. But that would be the other type. So for this type, if I had from 2 to 4, okay, like negative 6 to 2 or 0 to 2, I like both, right? And then what's another way? Oh, this one only has one. I can't do the third one with this one. Sorry. If I added, here, let's do this. Let's make this x plus 3 down here. So it's 1 over x minus 2 times x plus 3. So if it went from negative 3 to 2, problems. Yeah. It's going to be bad. It's going to be bad. Sorry, it was 1 over x minus 2 times x plus 3. I know, I just squished it in there. And the limits for the integration were from negative 3 to 2. So you would be going from one vertical asymptote to another. Okay, you guys know the second part of this, right? What are the 3 steps? I'm not even saying what that is. But the first type, let's just draw a little. Oh, is it it's a gesture summary? I never filled it in? Okay, then forget this. Let's go. Let's get to an example. Yeah. Case number 1. Okay, so case number 1, you got a vertical asymptote at one of the endpoints, or one or both of its integration. Okay. So, wait, I didn't do the case where it was in between. Okay, we'll do that too. No, I think we did do it. Never mind. Okay, here it goes. Same steps. Same steps. First step is the replace. Now, this time we're not going to be replacing the infinity or the negative infinity with L. 0, because that's the problem child. That's the one that makes the denominator 0, right? So we'll say from L to 1. Because at 0, that's where we'd have the vertical. Okay, step 1, check. I integrate ln absolute value of x from L to 1, which is equal to ln of 1 minus the ln of the absolute value of L. And what is the ln of 1? 0, so we just get negative ln of absolute value of L. Take the limit. It is t time. I like that. T time. So now we want to take the limit of negative ln of absolute value of L. But as L approaches what? Yeah. Oh, yeah. Now, just one thing technically. We're going from 0 to 1. If you think about because we're going from 0 to 1, we're taking the limit as L approaches 0, but we only have to worry about it from the right. So we're trying to get this area on this side. We're approaching the L values approaching 0. It really only has to be to this side. You don't have to worry about that, but it's important as far as technically. What did I just do here? Oops, I crossed those things. Well, the reason is because negative ln of a number that's approaching 0. If it's a natural log graph, you can't approach it from the left, right? That's why I'm saying that. Yeah, it doesn't exist. But you do technically we're only approaching it from the right, but I don't. Well, I guess we'll do that here, but you don't have to. So it makes sense. Now, if I just asked you for the ln of a number that's getting closer and closer to 0, what would you tell me? Negative infinity. So what is the limit of negative ln? Positive infinity. So what do we say about this definite integral? Divergent. Right. Let's do another one. Enjoy this. Yeah, they're fun. So just so you realize what we just found out, if you looked at the graph of y equals 1 over x, and you tried to collect the area from the vertical asymptote to 1, no, you can't. You can't. Don't even try it. You get infinity. Okay. All right. B. This is the bad one. Should we skip B or do we? Yeah? Want to skip? We'll do them both separately. We'll do it. All right. We'll just do them separately. But let's break it up. Where do you want to break this one up? 0. Because we have vertical asymptote at negative 1 and 1. So we're going to break this up into the definite integral from negative 1 to 0. 1 over rad 1 minus x squared. Plus the definite integral from 0 to 1. 1 over square root of 1 minus x squared. Okay, so for the first one, let's take care of the r step. Please. Who are we replacing with the first one? The negative 1. So it's going to be the definite integral from L to 0. And that's stuff. And on the other one, of the definite integral from, which one replaces 0 to L. Oh, I like this one. This is a good one. Yes. So you saw that, and you're like, ooh, let's get to it. Okay. All right. No, you said let's do it. Okay, let's integrate. So I'm hoping that you guys see that that's the inverse sine of x. Yeah, we do. And we plug in the upper or lower and subtract. What is the angle whose sine is 0? And you're only allowed to choose angles for sine. You're only allowed to choose angles again for negative pi over 2. Pi over 2. This means the angle whose sine is 0. Are we okay that that's 0? Okay, let me make sure. So this is 0 minus the inverse sine of L. Or just the inverse sine of L for this one. Let's do the other one. Same thing here. The inverse sine of x. This one is 0 to L. So we get the inverse sine of L minus the inverse sine of 0. So this one is just the inverse sine of L. The one over here turned out to be, yeah, this was negative inverse sine of L. Now let's take the limit. T-tan. Like, for this one over here, we're going to take the limit of negative inverse sine of L as L approaches negative 1. Okay. Now I need you to really think about that sine curve. Forget about the negative in front. What is the angle whose sine equals negative 1? Negative pi over 2. Now, that would be the inverse sine of negative 1 is negative pi over 2. So positive pi over 2. Yep, whatever, you have to split it up. No, just kidding. No, I just made that up. This one, you're taking the limit. I know, because you're writing that down. That you pick up the pen for, I know. This one, L was approaching 1, positive 1. So the angle whose sine is positive 1 is pi over 2. See that? Right, so this is pi over 2. And yes, remember we were adding these two. And so we add them, we get pi. These are fun. You like these? Same sheet for tonight. You're going to try some of these. No, like, well, oh, the answer is pi. Because each of them turned out to be pi over 2. What's that? Yeah. It has A, B, and C on it? Oh. Oh. Oh, yeah, don't do whatever the part what was part C anyway? You don't have to do that. Can you, I don't have that for, I want to do this. There, sit down. You see. So wait, you have how many problems? 4? And can I just see what you have it very handy here? So the 15 was the one, oh, one of them I think you can't do. Oh yeah, don't do C on number 15. Don't do it, because it's something called the shell method, and you never learn that. Oh. Okay, let's summarize this. I think we can do it. An integral is called improper if either or both of the lengths is infinite, limits of integration, or if the what is infinite. The function you're integrating, we call that the integrand. Integrand. To evaluate an improper integral, use written. If we get plus or minus infinity, we say the integral diverges. If we get a constant, we say the integral converges to that constant. All right. Okay. Alright, let me stop this.